All right, let me say this again. Good morning, everyone. Thank you for joining us on the RC Design Concrete class. Very happy to have you all back, safe and sound, and hopefully motivated and well rested for the new week and coming exam. All right, coming exam. Now, before we get all started, I want to make a quick announcement on the exam. Exam number 2 is going to mainly cover the one-way slab and the shear, one-way slab and the shear. And I will finish the last part of one-way slab, which is moment distribution. So you should be able to have all the knowledge that you should already have all the knowledge needed for the second exam. And we will go over some of the old exam today, just to give you a taste of what it looks like for the exam. Now the exam is scheduled this Thursday, 1 to 4 p.m. again. And we'll have an office hour tomorrow. So apart from what we review today, I will also add some information tomorrow. So if after today's lecture, if you have more questions or concerns, please join us on the during the office hour tomorrow. Okay. All right. Before I get other things going, any questions for me so far? Anything about exams and homeworks and all that?
Professor,
Yeah.
did you say you were going to change the last quiz date, or did I mess that one up?
I will take a look at the quiz 8. I think most of us have turned in. And if we were to change the quiz, I'll send the email. Okay.
All right. Yeah, I thought that since it was due during spring break that you had moved it.
Yeah,
So
I
I
I
wasn't
thought
sure.
I thought I did, but I may have forgotten that during the grading during the spring break. So let me just take a look at that. Okay. And by the way,
Thank
I
you.
finished all the grading. I just haven't finished all the updates yet, but you'll see them today latest. All right. Okay, any other question? But for the homework, all you need is mainly on the shear part. So it should be towards homework number 6. Okay, now one-way slab, I don't think we have time to let you finish the one-way slab homework. So during the exam, I will not give very hard questions. You will find very simple questions in the form that from the lecture notes. All right, so let me just add that information. Okay, all right, any other question for me before we continue? Are we good? All right. Okay. Well, let me coming back to the lectures of ton of stuff to cover today. Okay. So let me do this, sharing screen. And again, welcome to email me if you have any questions. All right. Okay. So if you see my screen, here's what we left off from last lectures. Okay. So we talk about one-way slab. Specifically, we're going to talk about the moment distribution. All right, the moment distribution. And then let's take a quick review, right? So what we have talked about last lecture. So one-way slab, right? Remember one-way slab, meaning it bends along one way. It bends along one way. Needless to say that we need to provide two-way reinforcement. But from previous lecture, we said that one-way slab, meaning we provide flexural reinforcement or longitudinal reinforcement in the bending direction, and we provide the temperature and shrinkage reinforcement in the transverse direction. All right. So indicated as color as blue and red that you provide different reinforcement. And if you forgot how we determine that, please see the previous lectures. All right, so that's about the calculation details about one-way slab reinforcement configuration. Now we went down and talked about the continuous one-way slab, right? The difference between the reinforcement we talk about and the lecture content today is the condition, the support condition. Now previously we talked about the moments calculated using the simply supported condition. But for continuous one-way slab, that means the support are spaced apart and in continuous fashion. So in this way, we cannot use the simply this equation for moment calculation. They use different equations, all right? And then we talk about how we're going to determine the moment distribution per ACI 318 8.11.2 that says that there are two parenthetic configurations for determining the moment. One is the factor dead load on all spans, meaning you put this black distributed load on all spans, and you put this blue factor live load on the adjacent span to get the maximum moment at the support, to get maximum moment at the support, all right? And then you have another pattern, which is a factor of dead load, but with a live load on the alternative span, right? So this, you get the maximum positive bending moment, you get a maximum positive bending moment at the middle span. at the middle span. So you may ask, what is the purpose of doing this, right? It's more like playing a puzzle, right? A jigsaw puzzle, just put pieces together. Well, why we need to do this, right? The reason is that this is one of the figures I got it from the textbook, and this showing you the alternative loading patterns for it. So the reason for this is that if you see from the first picture A here, we have all dead load exerted on the span, right? We have alternate spans loaded, right? So when we have alternate span loaded, we make sure that there were maximum exterior moments, maximum exterior moment. All right. Now you say, okay, what's the difference if I load them all? If you load them all, for example, if we put another distributed load in the middle span, you will reduce the moment at exterior ends. And that's adversary, right? That's not something we want. We want a maximum moment to design for. So the alternative span bending give you the maximum moment at end, at end. Now for this, right, we have a centrally loaded condition, right? This give you the maximum bending moment here. Well, actually, let me reversely draw it here in the middle span, and also give you the maximum bending moment here in the interior span, right? So these, and the last one is on the adjacent span. We have mentioned that before. So all these are the loading patterns, and don't have to worry about it. That's just for your information, right? FYI, and you just need to know this, have a more of general knowledge. You don't have to remember exactly how this pattern was decided, okay? This just to give you a sense of that. You cannot just arbitrarily load the beams to get the max moment. There are regulations you have to follow. Okay, now this is very complicated. Theoretically, you should just do the pattern, find out the bending moment, and determine what is the maximum bending moment and what is the maximum shear force, right, on the continuous span. And that is too much work and too complicated on site, right? It takes forever to figure it out. So ACI says, you know what? Let's do a simplified version. All right, that's what we like the most. So in ACI, I believe table 6.5.2, you find this ACI coefficients. You find this coefficients. All right. So what are the coefficients? First, take a look at this, right? If you want, I want to read the table, right? I want to read the first line, which is, excuse me, positive moment. Where are the positive moments, right? It can be at end spans, and at the end spans, we talk about the conditions. If discontinuous end is unrestrained, this is very puzzle word, right? What do you mean by discontinuous end is unrestrained? Means if I have a simply supported condition, is that right? Right? This is called unrestrained. The word restraints refer to moment, refer to rotation, moment, rotation. They're the same thing, right? So if my bending rotation or moment is constrained, that means it's restrained. If it's not, then it's not restrained, right? So in this case, discontinuous end simply means simply supported and unrestrained. So in this way, you use this. What does it mean? It means I'll have to use 1 over 11 omega u to zoom out and to show you omega u is the factored ultimate applied load distributed, and ln squared. What is this ln? Ln is a span length. Ln is a span length, which I will explain more in details, okay? But that is, I can assign this as my maximum bending moment right here, okay? As my maximum bending moment right here, all right? And if it's discontinuous and it's integral with support, I will use this number, which is 1 over 14 omega u ln squared. All right. And for interior spans, I use 1 over 16 omega u ln squared. And for negative moment at exterior surface, face of the first interior supports, 2 span, more than 2 span, yada, 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 too long, right? Too long, no patience, right? We have no patience. We want instant gratification, right? We don't want this table. It's too complicated. So ACI says, you know what, guys? I can make it even more simple, right? I can make it even simpler for you, right? So this is the figure we're going to use for our homework and for this lecture. Now you can see this, I have different configurations. I have different configurations, right? So let's read these figures all together, right? Figure A, it says more than two spans, right? So if I have more than two spans, like so, right? So this is one span, this is two span, this is three spans. For your information, right? For your information, what is Ln? Be careful, okay? Ln is the clear span between them, right? This is Ln, by the way, okay? This is Ln. Of course, this is another Ln, right? They have same length or they may not. All right, they may not. But rest assured, I can have all these factors, right? And you see all these are numbers: 0, 1 over 11, 1 over 24, 1 over 14, 1 over 10. What do they represent, right? What are these numbers? By these numbers are prefactors of front in front of omega u ln squared. Okay, so meaning everything has to be 0 multiply omega u ln squared, 1 over 11 multiply omega u ln squared, omega u ln squared, omega u ln squared, so on and so forth. Okay, I don't have to elaborate, you understand, right? So these are just coefficients, right? And that's why ACI called it moment coefficients, moment coefficients. All right, now let's read a little bit fine print, right? Take a look at figure 1, sorry, figure 8 again, figure 8 again. Okay, let me zoom in and you can see this clearly, hopefully. And now in figure A, right, it says here in figure A here, I have 3 rows of numbers, 3 rows of numbers. All right, so this is really a lazy way of writing it. Okay, so let's go row by row. So first row I label as 1, said discontinuous and unrestrained, right? We have explained that. What does this mean? It means it is simply supported with a simply supported condition like that. Okay, so this means this is number 1. All right, so for number 1, at this called surface or face of the exterior support. Okay, this is called the face of exterior support, by the way. Okay, exterior support. Okay, this is called the face of exterior support, and these are negative bending moment, folks. These are negative bending moment. Okay, so there's a negative sign in front of it. So the first bending moment here is 0. All right, and the middle span it will be positive. So sorry, excuse me. So it's 1 over 11. And the rest of it, this is minus 1 over 10. This is minus 1 over 11, positive of 16, minus 1 over 11, minus 1 over 11. Okay, now I didn't put the sign up there, but I put the sign here. So you can see that the pattern of the signs are whenever you have the support, you have negative sign. Whenever you have midspan, you have positive signs. All right, so just to get more clear, so this is minus 1. Okay, this is positive, this is minus, this is minus, this is positive, minus, sorry, minus, minus. Okay, so that's how the first row reads like. Now the second condition, second row means spandrel. What do I mean by spandrel? Spandrel means L shape. Spandrel means L shape. That means I encapped it. There's no column on the top of it, and this is pour monolithically. This is pour monolithically. So under this condition, the first number will be 1 over, first number will be 1 over 24. Middle span is positive 1 over 14, negative 1 over 10, negative 1 over 11, positive 1 over 16, negative 1 over 11, negative 1 over 11. All right, so that is for spandrel, means case 2. All right, for case 3, and this is negative 1 over 16, positive 1 over 14, negative, this software sometimes it's crazy. Hold on. Give me 1 second. Let me fix this. Okay, so this is negative 1 over 10, negative 1 over 11, positive 1 over 16, negative 1 over 11, negative 1 over 11. And don't forget, all of them are coefficients in front of omega u, ln squared. Ln squared. Okay, so that is how you use this table. This is how we use the table. All right, so this is only table A, right? How about table B? Table B meaning only 2 spans. If I only have 2 spans, right? And you can also get the coefficient in front of like that. All right, now this is slab with spans less than 10 feet, right? That is if my ln here is smaller than 10 feet. I can use this table. And this table here, last one but not least, is I column bigger than I beam. That means when I have a column and beam joints, right, at this condition, I have a moment inertia for the column is bigger than moment of inertia of the beam, and actually 8 times of that. 8 times that. What does it mean? Means that most of the moment will go to the slab. Most of the moment will go to the slab. All right. So you have a smaller number at the support, but larger number at the middle span. Larger number in the middle span. All right. But anyway, sorry, reverse. You have a larger number at the support, smaller number at the middle span. Yes, that's right. Okay, so this is our special occasions. So you may ask, and I don't like this software cannot recognize images, but anyway, so you may ask, which table are we going to use, right? So for our intent and purpose for exam, right? Our intent and purpose, we usually confine ourselves to figure 8. Sorry, figure A. We always like to give problems related to figure A, figure A. Okay, so this will be the figure or table you will need for homeworks and exams. All right. Okay, so I just went through all this in the speed of light, right? Very fast. And you say, okay, what this does to do with us, right? How this help us, right? So let me show you an example, right? Let me show you an example. All right. But before I show the example, I want to lay down some rules. Lay down some rules, right? What are the rules? These are nice coefficients. These are nice coefficients, right? So they also call it approximate. They also call it approximate analysis, all right? You may not have found out that, but these are simplified calculations, right? Meaning you don't have to draw moment shear diagram again, and you just follow the coefficient to find these numbers, which are pretty fast, and that's why I call it approximate analysis, meaning you don't have to actually do the calculations. But this comes with a price that you have to have limitations, right? What are the limitations? So ACI says, right? ACI, this is called moment coefficients. ACI moment coefficients can be applied, by meaning that beautiful table only can be applied under such conditions, right? To determine the maximum moment, max moment, and shear, okay, in continuous beams and slabs, one way, by the way, okay, subjected to vertical loading, right? Not horizontal, but vertical, aligned with gravity, right? Aligned with gravity, okay? But with following limitations, right? With following limitations, right? So what are the limitations? Meaning criterions that you have to satisfy to use it, right? So following are the limitations. First one, let me use different color. Sorry, folks. These I need you to remember, okay? Let me just put a asterisk mark here. Remember, as some wise guy says, this will show up in exam, right? This will show up in the exam, right? So first, it got to be 2 or more spans. It got to be 2 or more spans. I mean, I have to have, I want to use a simplified drawing, okay? I want to use a simplified drawing. So this is 1 span, this is 2 span, and continuous, right? 2 or more, right? 2 or more spans, right? Second, the span lengths, right, are approximately equal. Okay, and exceptions, right, with longer of the two adjacent spans, longer of the two adjacent spans, not 20%, okay, not 20% greater than the shorter span. Okay, what does it mean by that? What does it mean by that? Okay, means that, right, if I have two or more spans, right? If I have two or more spans. Now, if I were to calculate moment coefficient, say here, right? If I were to use it, let's say I have ln1 and I have ln2. And just to make it clear, let me draw a shorter span here. Okay, and etc. etc. That means my ln1 has to be smaller or equal than 1.2 ln2. Okay, this is what it is, right? Of course, this is when ln1 is bigger than ln2. Okay, vice versa, because these can switch places, right? Either one of them. Okay, so this is another limitation. Folks, just give me 1 second. Let me shut the window so we have less noise. We'll be right back. All right, sorry about that. I'm back. So this is the limitation on the span length. It means that we prefer the adjacent span has to be about the same size, about the same size. All right. Okay. Number 3, best to be uniformly distributed load. Uniformly, my spell is out of place after spring break. Uniformly distributed. Okay, that means I want to see a loading that is uniformly distributed. Okay, any concentrated force cannot be applied here. Any concentrated force cannot apply here. All right, and number 4, right, just to complete the picture, that means I'm referring to this distributed load. I'm referring to this distributed load. So if I have any concentrated force, this is no. Okay, cannot have concentrated force. All right, so number 4 here, that the live load does not exceed 3 times of dead load. Okay, and this is unfactored. This is before you do factor. Okay, that means live load is smaller than 3 times of dead load. Okay, unfactored, no 1.2, no 1.6. Okay, and number 5, and this is called prismatic members. What do I mean by prismatic? These are spherical. Yeah, well, this is talking about, for example, this is my slab, right? I need to have support. So my support has to be prismatic. Okay, so something like this, and will not work, right? Will not work. Has to be prismatic. Has to be prismatic members, right? Squared, right? Squares, right? Now, last but not least, okay, if 1.4 dead load governs, that means if this is bigger than 1.2 dead plus 1.6 live, okay, then moment coefficient cannot be applied. Cannot be applied. All right. So that's it. That's all the list, right? Such a long list, right? Such a long list. But these are the rules that if we want to have a simplified approach, right? So let's review them. 2 or more spans easily satisfied, right? Span length, right, has to make sure one is within 20% of each other, right? One is within 20% of the adjacent one. And uniform distributed loading, no concentrated force can be allowed, and live load does not exceed 3 times of dead load, which most cases are. And prismatic members, everything has to look square, cannot be round, smooth shapes, unfortunately. And last is that the 1.4 dead load has to govern, right? 1.4 dead load has to govern. Sorry, cannot govern. So cannot govern. Okay, 1.4 dead load cannot govern. If governs, you cannot use moment coefficients. All right. So these are the rules. These are the rules, and these are the rules you need to check prior to solve problems, prior to solve the problem, or along the way. Okay, along the way. So let me pause here. Any questions so far on these rules? Any clarity needed on these rules? All right. Okay. If not, let's show an example, right? Let's show an example. So let's take a look. If I have a problem to solve, right? So example, okay, example, we want us to determine the design moment, okay, at the critical sections, okay, using the ACI coefficient, ACI moment coefficient. Although we know that they apply to shear as well, but in our course, we're not going to ask you guys to do shear, okay? Following one-way slab, and we will let you know it's a one-way slab, okay? So you don't have to judge yourself mostly. And given the property that concrete is a 4 KSI strength in compression, and the steel is 60 KSI in yield strength. All right. Okay, so this is a problem. First of all, let me show you the image, right? What does it look like? I want to show you the one-way slab, right? So this is the one-way slab and the edge of that and supports, right? So if I want to use ACI moment coefficient, I need to have 2 or 3 or more than that, right? 2 or more spans. So I want to have end support like this, end supports like this. I have a middle supports like this, have another middle supports like this, another middle supports like this, and kept it. So this is my one-way slab. All right, and 3D effect, 3D effect, 3D effect. Okay, and you immediately can tell this is the bending direction, right? This is the bending direction. So let me just draw here. This is the bending direction. So that is transverse. So this is transverse. This is longitudinal. Okay, this is longitudinal. And when we talk about span, here are the numbers. First of all, the support has a width of 12 inch. Support has a width of 12 inch, all of them, right? 12 inch, 12 inch. Okay, and the distance between the center of the support, these are all center line here, okay? These are all center line here. Okay, these are center line here, okay? Distance between them are such. This is 13 feet, okay? 13 feet, and this is 15 feet, and this is 13 feet, okay? Before I move on, right? I want to calculate the span length. Let's call it Ln1, that equal to what? 13 feet, right? Minus 6 inch over here, minus 6 inch over here. What I got? I got a 12 feet, isn't it? I get 12 feet. So this is 15, so Ln2 equal to 14 feet. And this is again Ln3 equal to 12 feet, right? So Ln is actually the clear span, right? So Ln3, Ln2, just so you see them, visualize them, okay? And these are clear spans, right? So that is the geometry. That is the geometry, all right? And to get more detail, right? I know the height of the flange, right? HF, right, is here, okay? And I have a total section height, which is H, is right here. All right, and let me give them numbers. So HF in this case is 6 inches, right? Yes, 6 inches. The height, total height is 22. And don't forget D, which is depth of that, right? Here, depth of it is 19.5 inch. Okay, so these are the numbers. These are the numbers, geometry. All right, then we're going to design for it. We're going to design for it. Okay, now this is a little bit hard to do. This is a little bit hard to read, right? I want to do a simplified drawing. Okay, so how do I do simplified drawing? I just get the interior. Let me just clear this out, right? Let me use the red color so you see better. So I get the interior lined up. Okay, so I see it has more like this kind of spans, right? So a simplified approach, right? Simplified approach would be something like this, right? Simplified drawing. And this is my reaction force, and this is my reaction force, okay? And then I have another reaction force here, okay? And then this is my Ln1, right? Ln2 and Ln3. Right? And I'm trying to find out the moment, right? So before I start doing it, I can see it already. The moment diagram will look like something like this, right? So negative, positive, negative, positive, negative, positive, negative. Okay, so I'm trying to find out this number, 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 right? So 1, 2, 3, 4, 5, 6, 7, 7 moment coefficients. Okay, so this is our problem. This is our problem. All right. Okay, let's try to solve it step by step. But before I go on, let me just add one more information. The live load is known and is given, that is 150 pounds per square foot. And the dead load is snow load, right? Dead load is a self weight. No, self weight, right? Self weight. Let me just write it clear so sometimes get confused. Self weight of concrete, of course, right? Okay. All right. So these are all the information we need. All right. So solve this problem. To solve this problem, first, we need to confirm. We need to confirm that the ACI moment coefficient can be applied. Can be used. Right? Can be used. Right? So let's check the criteria one by one. Let's check the criteria one by one. Right? So first of all, so 1.1, is it 2 or more spans? So 3 spans. Okay, check. How about number 2? Is it one span shorter than the other, more than 20%? So Ln1 is 15 feet, right? Divided by 13 feet. That's a longer one. Sorry, I use the nominal span length, but that's fine, okay? That's fine. I can use 14 by 12. Sorry, let me use this number to be close. This again, all right? So allow me to recalculate this calculator. Give me 1 second. So 14 divided by 12, okay, 1.167, okay? And this, ladies and gentlemen, is definitely smaller than 1.2. All right, so check. Now, next one, 1.3, right? Boring list. The dead load, right? And the live load has to satisfy a certain requirement, that is live load is no more than 3 times the dead load. Right, and this is unfactored, but we don't know them, right? We don't know them yet, right? We only know the live load is 150 pound per square feet. How about the dead load? All right, pay attention, folks. The dead load simply is HF, which is the height of the slab, multiplied by the density of the concrete, or specific weight, basically. Specific weight, okay? I did not mention this term from previous lecture, so make it confused, okay? This is called specific weight of concrete. And in our lecture, we use 150 pounds per cubic feet. Okay, so that's that, right? So bring the numbers. I have 6 inch multiplied 150 pound per cubic foot, right? I got what? I got 75 pound per square foot, All right, so apparently live load, okay, divided by the dead load is what? Is 150 divided by 75 is 2 times. All right, so smaller than 3 and check. Right, that's fine. All right, and then what are the number 4? Let me see. Number 4, uniformly distributed load. We covered that already. That wouldn't be a problem. And actually, let's check. Is it prismatic? Well, look at the picture, right? Pretty square to me, right? Pretty square to me, so check. Oh, check, right? How about the dead load? So how about the 1.4 dead load governs or not? Isn't it? So check 1.5 dead load. Sorry, 1.4 dead load is 1.4 multiplied by what? 75. Okay, so that is what? Ladies and gentlemen, give me 1 second. Get my calculator out again. So this is 1.4 multiplied by 75. I have 105 pounds per square foot. Now 1.2 dead load plus 1.6 live load equal to 1.2 multiplied by 75 plus 1.6 multiplied by 150. 150, yes, 150. What I got? So the first one, 1.2 multiplied by 75, that's 90, yes, and 1.6 multiply 150, what I got? 240, so I got 330, which is definitely bigger than 1.4 dead load, which is 105. Okay, so check. 1.4 dead load does not govern. All right, so at this point, I'm pretty happy, right? I said, you know what? Can use ACI moment coefficient. Okay, moment coefficient. Now, you may think this might be a small deal, but if you were to do senior design with me, and definitely I will let you use software to determine all the moment and share coefficients, because most likely ACI moment coefficient will not apply, and you have a lot of work instead of this. Okay, so this is godsend, right? This is very good news. We're very happy. Okay, so we can use it, simplified approach. All right, so now that's first step. Second step, determining it, right? So now we can use the table to determine the coefficient. Sorry, my spelling, sometimes I get a little bit short patience. Okay, we can determine the coefficients, right? And like I said, we will use the simplified drawing. We'll use the simplified drawing because the original drawing is too complicated, right? So just a straight line. Straight line will have 3 spans, right? So get the support here, support here, support here, support here. And I have LN1, just know that 13 feet, LN2, 15 feet, LN3, 13 feet again, right? And let me just put numbers on them so to differentiate. Let me put A here, B here, not B, B here in the middle span, okay? And this is C here, all right? And D here in the middle span, and E here, right? And F here, and G here, okay? Immediately, you will realize that this is symmetric, right? This is symmetric. So on the top of your head, you say, look, Bob, I kind of know already the coefficient of C equal to coefficient of E, the coefficient of B equal to coefficient of F, and the coefficient A equal to the coefficient of G. And good for you, right? If you spot on this, you're fine. Okay, if you didn't, that's okay. You can still use that table. You can still use that table. All right, so let's take a look what table we can use, right? So go all the way back, go all the way back. And this is the table we're looking at. This is the table we're looking at. This is the table we're looking at. Okay, so which row? Which row? So let's take a look. We set three conditions. Number one, discontinuous, simply supported. Number two, spandrel. Number three, column and slab joint. Which one do we have? We have number two. We have number two, spandrel, right? Spandrel. If you forgot, take a look at the picture, right? Take a look at the picture, right? Perfect spandrel, right? Perfect L shape spandrel here. So we're gonna go option two, right? Option two, right? So option two says this is a negative 1/24. And for your information, this is omega u L squared, right? Ln squared. Which one? Is it Ln, L2, L3, Ln1 squared? Okay, Ln1 squared, because this is the first span, support of the first span, right? Here, B, which is positive 1/14 omega u Ln squared. And which one? Of course, Ln1 squared. All right, so here, now this is the tricky part, right? At C here, I have a negative 1/10. I have a negative 1/10 omega u Ln squared, right? Ln squared, right? So you see this part, you confuse a little bit. Why this is 1/10? 1/10, right? Why this is 1/10? Because here, I apparently have 1/11 as well, right? I have two numbers. Sorry, let me take this. This is row two, right? Row two. So I have 1/10, I have 1/11. So what happened to the 1/11? Okay, in this case, 1/10 is bigger than 1/11 magnitude wise. Okay, so we opt for the higher number for design. Higher number for design. Okay, so here's the trick. So we're not going to do the complicated 1/10, 1/11. Instead, we're just gonna pick the bigger one and move on, right? We're just gonna pick the bigger one, move on. So this is 1/10 omega u Ln squared. But this presents us a problem. This presented us a problem. What is the problem? I have Ln, but I have two adjacent them, Ln1, Ln2. Which one to use? Which one to use, right? So here, this Ln here should be an average of Ln1 plus Ln2, okay? And this is at B, okay? All right, so that has to look out for it. All right, at C, sorry, not B, okay? C, at C, the span length has to be an average of adjacent span, okay? Now D, continue, this is easy, one positive or 1/16 omega u Ln2 squared. Again, E, we said, right? This is same as C, right? Remember, symmetric. So this is again 1/10 omega u Ln squared. But this Ln here would be an average. Sorry, cannot see this straight. So E here, Ln here has to be the average, right? So it has to be 1/2 Ln2 plus Ln3. That is the average. Okay. Now F here equal to B, so 1/14 omega u Ln3 squared. And G equal to A, that is minus 1/24 omega u Ln3 squared. Clear out this point. Okay. All right. As you can see, it's not too bad. As you can see, it's not too bad, right? So we have all the coefficient labeled. So at this point, some of you may say, you know what, we're done, right? No, not yet. We have to actually get the numbers. We actually have to get the numbers. All right. Before we jump in, right, I want you to pay attention. When I say this A, B, C, D, blah, 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 so on and so forth, this is actually the bending moment, and this is should be the applied, the factored, the U, right? So this MU at A, this is MU at C, this is MU at B, so on, so forth, right? So on, so forth. And we actually use omega U, right? What is omega U? What is omega u, right? So before we do that, let's calculate it. So omega u equal to 1.2 dead plus 1.6 live. Okay, so you bring the number in, so 1.275 plus 1.650. I got a final number to be 330 pounds square foot, pounds per square foot. And just in case, right, I want to use kips, so convert it back to 0.33 kips per square foot. Okay, kips per square foot. All right, so we are happy to use this number. Okay, and just for your information, we also has verified that this is bigger than 1.4 dead. Okay, this is governs, right? So we don't have to worry about that condition. We don't have to worry about condition. Okay, so give me a few minutes, right? 2 more minutes. Let me finish this, right? So with this, I can go ahead. So at A, mu would equal to minus 24, 1 over 24, and this is 0.33, right? Kips per square foot, right? Kips per square foot. That is kips linear foot, okay, per square foot and linear foot. Okay, don't forget this per foot. You say, why, Bob? Why do we have to use per foot? Think about it. When we say the moment distribution, right? When we say moment distribution, we always looking at a foot of unit strip. Just 2 minutes, bear with me, okay, folks? Unit strip, 1 foot. So whenever you do the calculation, you have to bring this per foot into this business, okay? So this is 13 feet minus half feet minus half feet, because that's the clear span. And I think that's not 13 anymore, isn't it? Because I believe we have done the conversion. So this is 12 feet, okay? 12 feet, the shortest span, okay? This is Ln1. And that equal to a minus 1.98 kips foot per foot, kips per foot. Remember this unit, okay? And then B, C, D, so on and so forth. Okay, so on and so forth. And I'm running out of time, so I'm just going to close here. I'll fill this number up in the lecture notes. So you can take a look at them. And you're welcome to stay. And if you have any questions or just want to talk to me. All right. Okay, so I'm just going to end the lecture here. And I will see you on Wednesday, actually tomorrow, office hour. I didn't have time today to go over the previous exam. I will do that tomorrow, office hour, and I record it and upload, okay? And if you didn't have time tomorrow, I'll do it on Wednesday as well, okay? Wednesday morning as well. Yes, I just said that, Louis. I'm gonna go over the exam tomorrow, Tuesday in the office hour, because I'm running out of time today, and I'll go over them again on Wednesday. Whenever I do that,
Sorry,
upload and record. Yeah,
I was
that's
typing
okay.
as soon as you said that. So
Yeah, that's fine. I
delay.
just want to
Okay.
review it. Yeah, okay. All right, so welcome to stay behind. Let me finish this, or we'll see you tomorrow, okay?
Do I just attend an office hour, your office hours then?
Yeah, you can do that. I'll record office hour actually.
Okay.
I will record office hour as well. Let me just, yeah.
Well, when exactly is your office hour? Is it like
2
in the
o'clock.
evening?
This is
Okay.
same Zoom link we use for lectures. You just join in, like pop in. I can see the notification whenever who's joining in.
All right. Thank you so much.
Not a problem. Yeah. Okay. Let me stop recording.